Imagine this. You're in 19th century London, and there's this young, impoverished bookbinder, completely self-taught.
Hmm.
But this guy is destined to become known as the father of electricity. Quite a leap, isn't it?
Oh, it's an extraordinary journey. I mean, from really humble beginnings, son of a blacksmith, apprenticed in a bookbinding shop, he really defied all the expectations of the time.
The social structures, the scientific hierarchies.
Exactly. His story is just, well, it's a powerful reminder that genius can pop up absolutely anywhere.
And what a story it is. So in this deep dive, we're going to unravel the incredible life of Michael Faraday.
Yeah, we'll dig into his, sheer genius and experimentation, that complex relationship with his mentor, Sir Humphrey Davy.
Oh yeah, that's quite a story in itself. Tumultuous is a good word.
Definitely. And, how his foundational ideas really became the blueprint for the whole electric world that people like Edison and Tesla later built.
Right. So our mission here is basically to pull out the most important bits, the key knowledge and insights from the sources we've looked at.
Kind of a shortcut for you, yeah. To really get a handle on Faraday's massive impact and, honestly, the surprising twists in his journey.
We want you to take away not just what he found, but how he actually changed our whole way of thinking about the universe.
That's absolutely how he thought was revolutionary.
So, okay, let's unpack his discoveries, dive into those dramatic personal conflicts that shaped him, and then trace how his fundamental principles really powered that whole war of currents that still defines our power grids today.
Sounds like a plan. Where do we start? With the big question of his time.
Let's do that. So, set the scene. It's around 1820. The Danish physicist Hans Christian Ørsted had just made this huge discovery.
Right, that electric current creates a magnetic field around it. A wire carrying electricity deflects a compass needle.
Exactly. Big deal at the time. But it immediately threw up an even bigger question, didn't it?
Oh, yeah. The one that became Faraday's, singular obsession.
If electricity can make magnetism...
Can magnetism make electricity?
That was it. The scientific holy grail of the era, you said.
Pretty much. Lots of brilliant people tried and failed. But Faraday, well, he delivered. August 29th, 1831, electromagnetic induction. That was the aha moment.
How did he actually do it? What was the setup for that experiment? His approach?
It was really ingenious. He took two insulated copper coils and he wound them onto opposite sides of a soft iron ring.
Okay, like a donut shape.
Exactly. Think of a simple donut, wires wrapped around two different sections. He connected one coil to a battery, the other to a galvanometer.
Which is just a sensitive current detector, right? To see if anything happened in the second coil.
Precisely. He was watching that needle like a hawk, looking for any flicker at all.
And what did he see? What was the actual breakthrough observation?
So this is the crucial part. The galvanometer needle only twitched, just momentarily.
Only momentarily?
Yeah. Specifically when he connected the battery to the first coil, or when he disconnected it.
Not while the current was just flowing steadily.
Nope. When the current was steady, nothing. The needle was still. And that was profound.
So it wasn't the magnetism itself, the static field.
It was the change. The change in the magnetic field that induced the electricity in the second coil. He even talked about it like a wave of electricity spreading through that iron ring.
Wow. That's a massive conceptual leap. So this idea that change is the key. What did that mean practically?
Well, it led directly to Faraday's law of induction. It's fundamental to all electromagnetism.
Okay.
Before him, scientists thought of electricity from batteries or magnetism from lodestones as these constant static things, just on.
Right.
Faraday showed the real action, the interaction, needed change, movement, fluctuation. It's like a light switch power isn't generated just by being on or off, but by the act of flipping it.
That flip in the magnetic field creates the electrical push.
Exactly. That change is what drives our world. It wasn't just a discovery. It was a total paradigm shift from thinking static to thinking dynamic.
And he didn't just leave it as a principle. He immediately thought, okay, how can I use this change creates power idea to make a continuous source?
Right away. That led straight to the dynamo, still in 1831.
The Faraday disc.
That's the one. Basically, the first continuous electric generator. It was incredibly simple, just a copper disc spinning between the poles of a horseshoe magnet.
So as the disc spins, it's constantly cutting through the magnetic field lines.
And inducing an electric current continuously.
So this was it. The first device to turn mechanical energy, the spinning, directly into continuous DC electricity.
Precisely. And the impact. Well, huge. It meant we weren't just stuck with chemical batteries anymore for continuous power.
Right, which were pretty cumbersome.
Very. This opened the door to large-scale generation using steam power, water power. Every single power plant today fundamentally still works on that basic principle Faraday demonstrated.
It's incredible. And what's really amazing is that he'd already figured out the other side of the coin like a decade earlier.
Yeah, back in 1821, turning power into motion.
The precursor to the electric motor.
Absolutely. His discovery of electromagnetic rotation, the experiment was so simple, so elegant.
Describe that one.
Okay, so he had a wire, right, dangling, so its end dipped into a pool of mercury.
Yeah.
And there was a magnet standing upright in the middle of the mercury pool.
Okay.
When he passed an electric current through the wire started to rotate continuously around the magnet.
Just spinning round and round?
Yeah. It was the first time anyone had converted electrical energy into continuous mechanical motion.
So you've got the motor in 21 turning power into motion, then the dynamo in 31 turning motion into power. It's just perfect symmetry.
It really is. And for Faraday, that highlighted this deep unity in nature, something he believed in profoundly.
That all these forces were connected somehow.
Exactly. It reinforced his conviction, laid a kind of philosophical groundwork for, later unified theories in physics.
Yeah.
Maxwell, Einstein. He saw the invisible threads.
Now, okay, beyond these amazing tangible inventions, he also gave us something maybe more abstract, but just as important. His field theory.
Yes. This might be his most revolutionary conceptual contribution. You see, Faraday wasn't happy with Newton's idea of action at a distance.
Like how gravity just works across empty space, with no explanation how.
Right. Faraday wanted a physical mechanism. How does the force get from A to B?
And that's where the famous iron filings experiment comes in, sprinkling them around a magnet.
Exactly, and seeing them line up in those distinct patterns, those lines of force.
We've all seen pictures of that.
But here's the thing. For Faraday, those lines weren't just like pretty patterns or mathematical aids. He believed they were physically real.
Physically real? How so?
He thought they represented a state of tension or stress that actually existed in the space around the magnet or the electric charge. This was the beginning of field theory.
That's a really counterintuitive idea for the time, wasn't it? People thought about forces between objects, not in the empty space.
Totally. And what's really fascinating is that Faraday basically proposed that the origin of phenomena, the real action, wasn't in the objects themselves, but in the field between them.
Wow. A radical shift in thinking, a whole new framework.
And this conceptual leap was absolutely essential. Crucial, because without Faraday's concept of the field, this idea that forces spread through space, they don't just act instantly. James Clerk Maxwell couldn't have developed his equations later on.
The ones that unified electricity and magnetism.
And light. Faraday essentially gave Maxwell the intellectual scaffolding, the physical picture he needed to build his mathematical masterpiece.
Amazing. And Faraday's genius wasn't just limited to electricity and magnetism, was it? He dabbled elsewhere too.
Oh, his breadth was incredible. He was a real polymath. In electrochemistry, for instance, he laid down the fundamental laws of electrolysis.
And he even coined terms we use constantly, right?
Yeah. Anode, cathode, electrode, ion. Think about that everyday chemistry terms from this one guy.
And chemically, he discovered benzene. That's huge.
Huge. And he was the first to liquefy gases like chlorine. He even played around with iron and nickel alloys, making an early form of what we now call stainless steel.
Just incredible range.
And then, something that really tied it all together for him, the Faraday effect in 1845, the magneto-optical effect.
What was that?
He showed that a strong magnetic field could actually rotate the plane of polarized light as it passed through, say, a piece of heavy glass.
So magnetism affects light.
Directly. It was the first experimental proof linking magnetism and light, a stunning confirmation of his deep belief in the unity of nature's forces. And again, another critical piece for Maxwell later.
You know, it's easy to just focus on the brilliant science, but his journey wasn't exactly smooth sailing personally, was it? Especially with his mentor, Sir Humphrey Davy.
No, that relationship is, well, it's a fascinating mix of genuine scientific mentorship and deep personal conflict. It's quite a drama.
So Faraday starts out, self-taught bookbinder, humble background.
Right. And he encounters Davy, who was basically the rock star chemist of England at the time, by attending his public lectures at the Royal Institution.
And Faraday, being Faraday, takes meticulous notes.
Beautiful notes, binds them into a book himself, and sends them to Davy, along with a letter asking for a job. Any job, basically.
And Davy was impressed.
Apparently so. Impressed by the diligence, the neatness. When a spot opened up for a lab assistant in 1813, Davy hired him. A moment that genuinely changed the course of science.
A huge break.
Massive. And a key early experience was when Davy took him on a big European tour, 1813 to 1815.
Scientific assistant, right.
Yes, but also, and this is heartbreaking, he also had to act as Davy's personal valet, because Davy's original valet refused to go.
Oh, wow. That must have been difficult.
Especially because Lady Davy, his wife, apparently treated Faraday purely as a servant, very class-conscious. But despite that indignity, the trick itself was scientifically priceless for Faraday.
He met Ampere, Volta.
Yeah, met the continental giants, immersed himself in the cutting edge of European science. Invaluable exposure.
So an amazing learning opportunity, but mixed with personal humiliation. What was Davy like? Why was the relationship so tricky?
Well, what's fascinating is Davy himself had risen from ordinary beginnings. But once he reached the top, he became incredibly status conscious. Brilliant, charismatic, yes, but also maybe insecure, very protective of his position.
Worried about challenges to his authority.
Seems like it. And he perhaps saw Faraday's rapidly rising star, his obvious genius, as a potential threat.
And this tension boiled over pretty early, didn't it? Around 1821, after Faraday's motor discovery.
Well, that's the first big crack, yeah.
Yeah.
Rumors started flying that Faraday had actually plagiarized the idea from William Hyde Wollaston, another top scientist.
And people suspected Davy was behind the rumors.
Many did. Wollaston himself didn't pursue it, thankfully, but it definitely damaged the trust between Faraday and Davy severely.
Like, it got worse.
Oh, yes. The chlorine dispute in 1823. Faraday successfully liquefied chlorine gas, which was actually something Davy had suggested trying. But when Faraday succeeded, Davy apparently demanded credit. Faraday refused. And shortly after that, Davy, as president of the Royal Society, is reported to have publicly accused Faraday again of plagiarizing Wollaston regarding the motor work.
Wow.
Publicly.
Yeah. Davy later tried to say the press misrepresented him, but the damage was absolutely done. The relationship was fractured.
And it all culminated in that really ugly incident known as the Black Ball during Faraday's election to the Royal Society in 1824. That sounds like the ultimate betrayal.
It really was. Faraday was nominated for fellowship, the FRS, a huge honor, in 1823.
And Davy opposed it.
Vehemently, as president.
Yeah.
He openly campaigned against his own protege. He even directly ordered Faraday to withdraw his application.
How humiliating.
Deeply. But Faraday refused to withdraw.
Good for him. His work clearly deserved recognition.
Absolutely. Despite Davy's active opposition, Faraday gathered, I think, 29 supporters. And when the vote happened in January 1824...
He got in.
He did, with only one single dissenting vote cast against him.
Let me guess whose that was. Widely believed to be Davy's. The sole black ball. After that, their scientific communication essentially just stopped.
Sad, really.
It is. Davy later assigned Faraday what seemed like trivial work organizing the library at the Athenaeum Club, spending years on improving optical glass for telescopes, which Faraday felt was a waste of his time, diverting him from fundamental research.
So if you step back, this conflict, it wasn't just personal, was it? It kind of symbolized something bigger.
I think so. It was like a clash between two eras of science. Davy, representing the older, patronage-based system, clinging to social status and power within science.
And Faraday embodying the new way, professional, merit-based, focused purely on the research.
Exactly, and you see that in how Faraday famously turned down a knighthood multiple times, refused the presidency of the Royal Society. He wasn't interested in the trappings. He was a true representative of this new scientific age.
So Faraday lays all this incredible groundwork. He reveals the fundamental rules of electricity, magnetism, the field. But how does that torch get passed on? First to James Clerk Maxwell, and then to, the big names of the electric age, Edison and Tesla.
Well, the key thing with Faraday, as we touched on, was his lack of formal mathematical training. His field theory was this powerful physical picture, a revolutionary way to think about forces.
But not expressed in equations.
Exactly. It lacked the precise mathematical language needed for really rigorous calculations and predictions.
And that's where the Scottish physicist James Clerk Maxwell comes in. His genius sounds like it was the perfect complement to Faraday's intuition.
Absolutely perfect. Maxwell took Faraday's physical ideas, the lines of force, the concept of the field, and he translated them into, mathematics, specifically for incredibly elegant differential equations.
Now known simply as Maxwell's equations.
That's them, and these equations did something amazing.
They unified everything.
Pretty much. They united electricity, magnetism, and light into a single cohesive phenomenon, electromagnetism.
Wow.
And here's the truly incredible part. Maxwell's equations actually predicted the existence of electromagnetic waves traveling through space at a constant speed.
And that speed turned out to be
Uncannily close to the known speed of light. It was theoretical proof that light is an electromagnetic wave.
which Faraday had suspected with the Faraday effect, but couldn't prove mathematically.
Exactly. And it raises that important question. How vital was this link? Without Faraday's intuitive leap, his concept of the field, Maxwell's equations just wouldn't exist. They couldn't have formulated it.
So that theoretical understanding flowing from Faraday through Maxwell was crucial for what came next, like AC systems.
Absolutely crucial. You needed that mathematical framework to really understand and develop complex alternating current systems.
Okay, so then we get Thomas Edison, the Wizard of Menlo Park. Not really a theorist, right? More the master of practical application.
Edison was all about practical application and commercialization on a massive scale. His genius was in system building, refining, making things work reliably and commercially.
So how did he build on Faraday?
Well, when Edison developed his incandescent light bulb system, he needed powerful, efficient generators. So he took Faraday's dynamo principle.
The spinning disk idea.
And his engineers improved it immensely. His famous long-legged Marianne generator was a direct engineering descendant of Faraday's original concept.
And Edison built his whole empire on direct current, DC.
Entirely. DC was a straightforward application of Faraday's principles. Generate current, send it down a wire. Simple, like Faraday's disk or a battery.
But then along comes Nikola Tesla, the dreamer, the visionary. He saw things differently.
Tesla was a deep theoretical thinker, much more in the vein of Faraday or Maxwell in some ways. He saw the big limitations of Edison's DC system.
Especially for sending power over long distances, right? DC loses a lot of energy.
Exactly. Tesla envisioned a far more elegant, efficient system using alternating current, AC. And his masterpiece was the AC induction motor.
Why was that so special?
Its brilliance was its simplicity and robustness. No brushes needed, unlike DC motors. Brushes wear out, spark. They're a point of failure. Tesla's design was inherently more reliable.
And how did it work? How did it use Faraday's ideas?
This is where it gets sophisticated.
Yeah.
It was a brilliant application of Faraday's induction, but filtered through Maxwell's field theory using polyphase, AC.
Okay, break that down a bit.
Tesla's genius was figuring out how to use multiple AC currents, out of phase with each other, to create a rotating magnetic field in the stationary part of the motor, the stator.
A magnetic field that actually spins without moving parts.
Exactly. Created purely by the alternating currents. And this rotating field then induced currents in the rotor, the spinning part, pulling it along, making it rotate continuously.
So it's using Faraday's induction, but in this really clever, dynamic way based on fields.
Precisely. A complex, elegant application of Faraday's fundamental insights, fully realized using the mathematical understanding Maxwell had provided.
And this difference, Edison's simple DC versus Tesla's sophisticated AC, led directly to the famous War of Currents.
The ultimate showdown. A battle for how the world would be powered. A battle really for Faraday's legacy.
So the key difference was?
Edison's DC was the direct, simpler application of Faraday's dynamo. Good for local distribution, like his early New York system. Tesla's AC, championed by Westinghouse, was a more complex but vastly more efficient application of Faraday's induction and field theory, grounded in Maxwell's math.
And efficiency for long-distance transmission was the key.
It was the knockout blow. AC could be easily stepped up in voltage for transmission over vast distances with minimal loss, then stepped down for safe use. DC just couldn't compete on that scale.
So AC won, becoming the global standard we still use today.
It did. And this is fascinating duality, isn't it? You have Edison, the pragmatist, optimizing the immediate application of Faraday's dynamo.
Making it work, making it sell.
And then you have Tesla, the visionary, pushing the conceptual boundaries, using Faraday's deeper field ideas and Maxwell's math to unlock the huge potential of AC.
Both standing squarely on Faraday's shoulders.
Absolutely. Both utterly reliant on the energy and the principles that Faraday first unleashed.
So when we look back at Michael Faraday, his contribution really is twofold, isn't it?
I think so. First, you have the tangible inventions. The motor, the dynamo, the absolute bedrock of all electrical technology, everything that spins, everything that generates power, owes a direct debt to him.
And second, maybe even more importantly,
his revolutionary conceptual shift. Field theory, that completely changed how physicists viewed forces, space, reality itself. He gave us the framework, the language to understand an invisible world that connects everything.
So while Edison and Tesla definitely built the machines, the systems, the infrastructure that powers our modern world.
Michael Faraday was the ultimate architect. He laid down the foundational ideas. He uncovered the fundamental rules of the game that both Edison and Tesla had to play by. Their creation simply wouldn't exist without his discoveries.
And his personal story, just incredible. From bookbinder to, well, the pinnacle of science. It remains one of the most inspiring journeys.
Absolutely. A testament to just relentless curiosity, sharp observation, and, frankly, the intellectual courage to challenge established ideas and trust his own insights. He really transformed the world.
So maybe a final thought for everyone listening. When you flip a light switch today, or you just look at the power lines stretching across the landscape, marvel at the grid. Consider this. It's not just the result of one invention or even two, it's the triumph of an idea. The idea that change, that dynamic flux Faraday saw, is the key to unlocking immense power. And that idea, that fundamental insight, was first truly illuminated by a man who taught himself science by reading the books he bound with his own hands. So maybe the question for us today is, what fundamental changes in our understanding right now might unlock the next revolution?